Hi class, welcome to lecture number 13 in refrigeration and air conditioning. So today we'll look at um, VCRS components part 2. So we'll be focusing on heat exchangers and fans. So if you look at the VCRS components diagram from the previous lecture, you can see that the heat exchangers are present at the condenser. So primarily at the condenser, it's a refrigerant to air heat exchanger, and you also have the evaporator, again air and refrigerant heat exchanger. Then you have sometimes not sometimes, in most scenarios you will have a heat exchanger on the suction line of the refrigerator, which either exchanges heat to the capillary tube or the actual line coming from the condenser. Okay, so this is basically a refrigerant to refrigerant heat exchanger. So primarily three types here. And the same thing is true for air conditioner. You have the evaporator, condenser, and sometimes you'll have the suction line heat exchanger. All right. Um, some advanced compressors have heat exchangers inside them, again to cool the refrigerant, but we're not going to look into that for now. And if you look at the other component, which is the fans that we are going to talk about, fans are present mainly for the um, air to refrigerant heat exchangers. So the cooling of the evaporator and cooling of the condenser usually is done with the help of fans. Fans also help cool the compressor. Compressors run extremely hot. So the same fan that cools the condenser tries to move some air over the compressor too to cool the compressor. Okay. All right. So this is the same thing that I just mentioned. The heat exchangers are three types. Evaporator, it absorbs heat from the refrigerator space, so it's usually between a heat transfer between the um, refrigerant and the uh, the air inside that cabinet. Condenser rejects heat to the surroundings, so the absorbed heat from the cabinet is taken by the refrigerant to the outside the cabinet, and then it's rejected to the outside temperature through the condenser heat exchanger. So the liquid suction heat exchanger is basically um, exchanges heat between the warm refrigerant fluid from the condenser with the cold fluid coming out from the evaporator, and it helps improve cooling capacity. Like I mentioned earlier in the class, you'll get more liquid at the inlet of the evaporator compared to having more bubbles or vapor, and it improves the cooling capacity because now you have more liquid for evaporative cooling. Okay, so now let's take a look inside what happens a condenser tube and an evaporator tube. So if you focus on the evaporator tube 4 to 1 or 4 to 1 prime or 4 to 1, what happens here? So you have two scenarios. You could have evaporators with tubes that are horizontal mostly, and some evaporators where the tubes are vertical. In either case, when the refrigerant first comes in, it's coming in as mostly liquid. Okay. This is not 100% true if we are talking about um, capillary tubes feeding the evaporator. And I don't want to go into that detail because it never comes in as liquid. It always comes in as two-phase. But for the purpose of understanding here, if you have some other way to expand other than the capillary tube, you could have mostly liquid coming in. Okay. And then the first vapor bubble forms because now what happens in the evaporator? Um, you're adding heat, right? So when you add heat, um, you're going in the right direction of enthalpy. So when you keep adding heat, you could have more bubbles forming. So as you keep on adding heat, the quality of the mixture changes, right? So you're sending a lot of airflow and thereby adding heat when you're in the evaporator. And as the flow goes from left to right, the um, the liquid starts converting into vapor. So it starts randomly first as bubbles, and then a lot of bubbles form, and then it forms a plug, which then forms a slug, and then it forms a wavy flow, an annular flow towards the end, and then it becomes fully dry gas flow. Okay. So a lot of bubbles form first. It's almost like how things boil when you're boiling water. So the bubbles form first, and then those bubbles become bigger and larger and become slugs. And eventually, when it's horizontal, you'll only have like a stratified flow where there is liquid only touching the bottom surface, and the top is mostly dry, right? When you're going vertically, you will not have an asymmetry like that. You will have annular regime as opposed to the stratified regime here. There's flow only on the bottom here. Here, there's flow everywhere on the perimeter. So if you took a cross section here, you'll see that the flow is everywhere on the outside. The liquid is mostly on the outside, and then that thin film of liquid fully vaporizes and becomes quality is one at some point. On the other hand, with condenser, what's first coming in a condenser is gas from the compressor. So when airflow goes on the condenser, the heat is actually going out. So you're removing heat. So colder airflow compared to the condenser will remove heat from the condenser. So as the um, heat is removed, you get a little bit of annular flow and a lot of drops forming inside, okay, like a mist. Eventually, uh, a lot of mist combine together as you keep going from right to left here. As you keep on removing heat, the enthalpy drops and it becomes more and more of a liquid and reaches the slug flow. It's almost like the reverse of this, okay? And then it becomes fully condensed. In some condensers, it never gets fully condensed. It ends up as a stratified regime where there's still some liquid and there's a flow of gas above it. Okay. All right. So you can do some calculations in Excel. You open up the Excel heat exchanger file and you can see what happens to the refrigerant and quality in condenser and evaporator by varying these inputs. Okay, so I have selected this for R134A. So what we have kept constant is the inlet temperature for the evaporator, and we are saying it's at around minus 20 degrees C. And we have kept the inlet quality as zero also. We've kept a constant mass flow rate, and then what we're doing is we are changing the heat added to the evaporator. So as we change the heat added to the evaporator, if we had only a little bit of heat, then the point 1 would be here, okay? If you add more heat, the outlet point 1 will be here. So that's what we are trying to see here. What happens to the outlet quality? So 100 watts gives you an outlet quality of 0.46, so that's somewhere in the middle. As you keep on adding watts, okay, more 200 watts, 210 watts, at 210 watts, you're almost close to the exit of the dome, 0.98. And if you add a little bit more than that, 220 watts, you cannot get a quality number anymore because you're getting an error from props SI because you're not two-phase anymore. And you can see that the outlet temperature also changed. Okay, the outlet temperature is minus 20 consistently when it's two-phase, and it became minus 11 when it was two-phase. So now it's superheated. And any amount of heat you add now will make it warmer and warmer. So by 240 watts, you're 12.8 degrees warmer. So you'll keep going outside the dome and your temperature will increase because now you're in sensible heating. You're not using the latent heat, you're in the sensible heating regime. The same is true for the condensing side. You could start with a 40 degree C condenser, and you could assume that everything that is coming into the inside of the condenser somewhere here is quality of 1. As you increase the amount of heat that is removed from the condenser, now this is not added, it's removed from the condenser. Um, you basically keep on going towards the left, right? At some point, if you remove, let's say, 160 watts, you're almost close to the end of the dome on the left side. If you remove further, now you're getting into subcooling. You'll get really colder and colder as you go past this dome and you keep on removing heat. That won't happen in a real condenser because real condenser cannot be colder than the surroundings because we are using the surrounding air to remove the heat from the condenser. So there is a lower limit. It cannot keep on going to a lower value like this. All right. Now, what are the types of heat exchangers? Um, there are three common types: paddle flow, counterflow, and crossflow that you encounter in refrigeration and air conditioning. In a paddle flow, a good example is this one here. You can see that the hot flow and the cold flow are moving in the same direction, which is left to right in this case. Okay, so they are exchanging heat while they're moving in the same direction. So that's called paddle flow. The opposite of that, when the hot fluid is going in one direction and the cold fluid is going in another direction, completely counter to each other, that's called counterflow. And crossflow is when fluids are perpendicular to each other. So one is going left to right, the other is going top to bottom. So paddle flow is not the most efficient. It's used in some compact air-cooled condensers and small refrigerant system. That is the least common type. Okay, paddle flow. Counterflow is a lot more efficient than paddle flow because of the average temperature difference it provides for heat exchange. Um, and the liquid suction line heat exchanger is an example. Shell and tube heat exchangers are examples. Plate heat exchangers are examples, etc. Crossflow is extremely common in evaporators and condensers where you have to cool the refrigerant using air. Okay, the fin tube heat exchangers used in air conditioning and household refrigerations are almost always in cross-flow configuration. Okay, all right. Now, these are some of the examples of the heat exchangers based on construction. So the first classification was based on the flow configuration. Now we are talking about based on construction. Shell and tube. So the one that you're shown here, uh, the name describes what it is. So there are a lot of tubes inside a shell. Okay. So the refrigerants, typically refrigerants flow to the tubes while another cooling fluid, usually water or air, uh, that is used to cool the refrigerant will flow on the outside. Most commonly it's water. So water-cooled condensers in chillers are the ones, the most common example of shell and tube heat exchanger. Okay. Tube in tube is basically, um, and by the way, you could have cross flow here. Okay, so if you look at the direction of the refrigerant flowing, the the fluid in the shell will flow cross to the main fluid and also um, counter. So it's a combination of counter and cross flow that happens in shell and tube. Tube in tube, it could have parallel or counter flow. An example is this. But majority of the time it is designed to be in counterflow. Okay, so liquid suction heat exchangers, subcooling systems, oil cooling, etc. Plate heat exchanger, which is the last one here, is basically a lot of small metal plates or thin metal plates are arranged parallel to each other, and there's space between them. There's gaps between these plates, and that's where the cooling fluids flow through. So in this case, the orange or the red represents one fluid and the blue represents another fluid. You can assume that the orange or the red is the hot and the blue is the cold one, okay? So you could see that they will alternate between each gap. So let's say if the hot fluid is going through this gap between these two plates, the cold fluid will flow in the next one, and then the hot fluid is going in the next one, etc. So it's designed by carefully arranging these openings between these plates. If you notice, they're always in counterflow configuration. So one is going down, the other is going up always. Okay, so counterflow, and primarily it's used for compact evaporators, condensers, etc. And it's primarily used for liquid to liquid. Okay, liquid to liquid heat exchange. It's not for liquid to gas. Um, Finned tube heat exchanger. This is primarily liquid to air heat exchange. Okay, liquid to gas, primarily air, and it's almost always cross flow. So you have a cross flow of air, and the refrigerant is flowing in this direction or this direction. So they are 90 degrees to each other. Okay, so this is the most common in condensers and evaporators that are air cooled. Microchannel heat exchanger is a type. Okay, by the way, the fin tube, the name comes from the fact that there's a tube and then there is fins. So these are the fins that exchange heat with the surroundings, and this is the tube. You have seen fins in several scenarios. If you look at your engine of a motorcycle, you'll see there are a lot of metal fins on it. Anytime there is a heat producing source, the easiest way to make it more efficient is to make sure you increase the surface area, and it's usually done by adding fins. Okay, so that's all there is to it for this one. Um, in this case, the microchannel, you have fins. You see the zigzag patterns? These are fins. Okay, those are fins. And then the channels are inside this, the gray colored section here. So if you take a cross section of this channel, if you cut it and look from the side, you will see there are several small channels, okay? Several channels. So these are where the refrigerant flows. So the liquid flows in these channels, okay? And the air flows through these fins. So this is also a cross flow, okay? Because the refrigerant is flowing in one direction from left to right, and the air is going normal to this paper. So it's cross flow. And it's commonly used in automotive, so in your car, and also in commercial refrigeration. All right, so these are to give you some idea about the construction for different heat exchangers, right? The largest one that you can see in this section is basically the shell and tube, okay? And microchannel ones and tube in tube ones could be really small. The plate heat exchanger also can be really small. Um, tube in tube fin tube comes in a wide range of sizes. The smallest ones are comparable to a plate fin, just like and are also comparable to microchannel. All right, so now let's look at specific heat exchanger designs in refrigerators. Let's start with evaporators. Evaporators have two types of designs. One is natural draft, means there's no fan, no fan, okay? Since they don't have fans, they rely on direct contact, which is conduction, and natural convection for heat transfer, okay? So what are these evaporators made of? They're typically made of aluminum plates, and they're also made of stainless steel sometimes. You basically make these things using a sandwich type design. You have two plates, an upper plate and a bottom plate, and there is some indentation on these plates for refrigerants to go, right? So you can see there are some projections here. So the refrigerant goes in this sandwich, inside the sandwich between these two plates. And you can see at the end, they're connected to tubes, two tubes, okay? So one is inlet and one is outlet. So it's going everywhere in the plate and providing cooling throughout the plate. And then uh, if there is no direct contact, you'll have convection, especially cold air drops down, right? So typically these kind of heat exchangers are placed on the top of the refrigerator, like in the freezer compartment, and then the cold air just drops down and cools the rest of the compartment. All right. Now, when you look at the evaporators with forced draft, in other words, with fans, this is how they look like. Okay. The most common one is the plain fin evaporator. So it is basically a tube and a fin around that tube that looks like that. Okay. And there are several fins. You could see from the side you have several fins. This is the typical fin density you will see. Okay. And notice how there's less fin density in the bottom. It's fin density here, and the fin density increases as you go towards the top. This clearly means airflow direction is like this. Airflow is through the bottom and it's going up, coming out. Okay. And you will see that happening in all types of plain fin evaporators where the flow is from the bottom and the fin density increases as you go to the top. Another one is the spine fin evaporator. It looks like spines wrapped around a tube. Okay, so in this case, um, if you look at the tube, it's almost like a lot of spines around the tube, like this. Okay, so it's basically made of aluminum ribbons, and then you cut the ribbons in such a way and make spines out of them, and then you wrap it around the tubing. So this tubing could be copper or aluminum. What you're seeing here is it's wrapped with an aluminum spine fin. These are typically more efficient. They're more, they provide more heat transfer than the um, than a plain fin. And in these cases, it's difficult to control the fin density as you go up. What they do is I don't have a view here, but they'll create a bigger gap between the tubes at the bottom. And as you progress towards the top, there is a smaller gap. So if you look from the sides, this will look something like an A shape. Okay, so the tubes are spaced farther apart um, at the bottom, and as you go, they converge, right? If you look from the side. So these are two um, types of tube fin evaporators that are primarily used in refrigeration systems. And the most common one is the plain fin. Now let's look at evaporators in air conditioning. Here, the most common one is the plain fin. Okay, there is also spine fin, but the most common one is plain fin. Um, and you can see the fin density is really high. It is really high compared to compared to um, refrigerators, compared to refrigerator evaporators. Why is that? I'll show you the exact reason in the next slide. But look at the fin density. You won't even be able to see the other side. That's how tightly the fins are packed. Okay. Um, Sometimes you have distributors where there are multiple circuits inside. Several. What that means is you have several inlets and several outlets. Okay. So you can see multiple inlets going to the evaporator. Anyway, so why is there a difference in fin density? This is why. So in a refrigerator evaporator operates at really low temperatures, okay, much lower than minus 20 degrees C. Okay, so it could be minus 35, minus 40, minus 30 in that region. The air conditioning evaporator operates somewhere in the 5 degrees C or above, so greater than 5 degrees C. So this has a lot of chance of icing. Okay, you can develop a lot of ice and frost in refrigerator. You don't have that issue. You will have condensation and water um, in air conditioning evaporator. So when you drive cars and you turn on AC, when you park the car, you'll see a lot of water coming out the bottom of the car because of condensation. But you'll never see frost like this. And because of this, most of the refrigeration air conditioners have a defrost heater to remove this ice. Okay. And since the ice forms from bottom up, initially it'll if you space the fins like this, it will help you operate with some amount of ice for some time before you have to defrost. If you didn't space it like this, you will have to defrost very often. You will maybe run for 6 hours and you will not be able to send any flow because everything is blocked. So you space the fins like this to capture most of the ice in the bottom fins, and you can still send some air, right? And you can operate for maybe 1 or 2 weeks and then defrost it. And you can see the defrost heater in all the refrigeration systems, evaporators. This is the defrost heater, okay? So you can see that one here too. There's one here. So that is the main reason why you cannot have very really high fin density in a refrigeration evaporator. All right. Now let's look at condensers. Condensers also in refrigerators fall into two categories: natural draft um, and forced draft. Condensers are typically made of steel tubes and steel wire fins. Okay, um, long steel diameter tube are basically bent in a serpentine onto which wires from the secondary surface area are welded. So you see these vertical wires, they're welded onto the serpentine tube. So first you'll bend this tube, okay, into this shape, and the refrigerant will flow in through that tube. The other tube is a solid fin. It's just welded fin. This is basically a fin, and this is a tube, okay? So it's basically wire fin type. Um, so this fin is wire fin, okay? It's just a straight wire, and usually it's steel. And if it doesn't have a fan and it's just attached to the backside or the inside of a refrigerator, inside wall, um, it's called natural draft condenser. If you want a forced air condenser or forced draft condenser, typically, again, majority is made with steel wire fin types, right? So wire fin condensers, they look like this. Now they have to be of different shapes, and you blow air using a fan through them. So in this case, it will be blown like that. In this case, it's probably blown like this. In this case, also, it's blown through the center and cooled. Um, so several types of shapes are possible with these condensers. There's also another fin called the spiral fin. So instead of the wire fin, in this case, you can see there's a spiral fin. Again, this is also steel condenser. Okay, this is also steel. There's aluminum condensers, which are basically microchannel condensers. This is relatively new. This started happening in the last 10 years or so. This is the same thing that we had discussed earlier about microchannel heat exchangers. So they basically help with having really small size but providing much higher surface area. Okay. Because it's made of aluminum, there are some issues with leakage and all that, but the industry is trying to solve all those problems. Condensers in air conditioners, there are two types: plain fin condensers. There are no wire fin, it's all plain fin, and microchannel. And primarily, it's all made of copper tubes and aluminum fins. Okay. Microchannel condensers are all made of aluminum, fins and tubes. Everything is welded together. So it looks like if you open your outdoor unit, it'll look like some L-shaped condenser. Sometimes it's just a straight paddle condenser. Sometimes it's U-shaped. So different shapes depending on the capacity of the system. Okay. All right. Now the third type of heat exchanger, other than the cross-flow heat exchangers that we discussed, is the liquid suction heat exchanger, which is typically a tube-in-tube counterflow heat exchanger. Okay. So in this case, there are two types. One where one tube is inside the other, and the other where one tube is welded to the other. Okay. So they are outside and welded. So this is most likely this is a capillary um, suction tube heat exchanger. Those are typically of this type. They're welded like this because believe it or not, this is more energy efficient, more better efficient heat exchanger when the tubes are of much different size and you're talking about a capillary tube. If you put a capillary tube in the center, it will not be very efficient heat transfer. On the other hand, if you're talking about a liquid line and the um, suction line, then a tube in tube is a better design. Okay, and both of them are counterflow heat exchangers. So the other thing to note here is it's between liquid to liquid, right? Liquid to liquid or refrigerant to liquid. This could also be liquid to gas, depending on whether the suction line has any liquid or not, right? But overall, it's refrigerant to refrigerant. Okay. All right. So that brings us to the end of the heat exchanger part of this lecture. All right, now let's look at fans. There are several different types of fans that are used in refrigeration and air conditioning, and these are some examples. But let's start with what exactly is the scientific definition of fans. As per the ISO 13349 standard, the definition of fan is it's a machine, um, rotary bladed machine which receives mechanical energy and utilizes it by means of one or more impellers. Impellers are the rotating blades um, fitted with blades to maintain a continuous flow of air or other gas. It doesn't have to be air, it's some type of gas, either air or something else, passing through, and whose work done per unit mass on that gas or air does not exceed 25 kilojoules per kilogram. So if 1 kilogram of air or a gas is passing through this rotary bladed machine, the amount of energy transferred through work to that gas or air should not be more than 25 kilojoules per kilogram. Well, what happens if it's more than that? At that point, it's considered a compressor, a turbo compressor, right? So that's too much energy to be considered as a fan. So if it is 25 kilojoules per kilogram, and we assume the working fluid is air, it has a density of 1.2 kilogram per meter cube. And what this means is this particular fan should not be able to provide a pressure change, total pressure change more than 30 kilopascal, okay, or 120 inches of water column. Now, what does this mean? The pressure ratio does not exceed 1.3 since the atmospheric pressure is 100 kilopascal. Okay, so if you're operating at atmospheric pressure and you have if a fan or a rotary bladed machine, then so assume that you have a rotary bladed machine. If you're operating at 100 kilopascal in air, across the fan you cannot have a delta of 30 kilopascal. So you cannot go to a ratio of 1.3. Okay, typically in atmospheric conditions, you cannot raise it to 130 kilopascal. All right, so how are these numbers calculated? First thing to know is power transferred to the airflow by a rotating machine. How do we calculate that? It's basically the work done. Okay, work done. It's basically pressure, volume, energy. Okay, so pressure, volume, energy is nothing but pressure times volume per second. Okay, and volume per second is the flow rate, Q. So power transferred to the airflow by the fan is nothing but total pressure times the volumetric flow rate. Now the volumetric flow rate is nothing but area times velocity. Okay, so you could write it that way too. Now what is the work done? The definition is based on work done. So the work done is basically you have to multiply this per time. You have to multiply with the time factor. So supposedly you're operating for time t, then the work done is basically PT AV times T. Mass of the air moved in time T is basically rho AV times T. So the work done overall is can be written as this if you replace this T with mass by rho AV. Okay, so now everything can be cancelled here. AV can be cancelled, and then work done per mass, work per unit mass is nothing but total pressure by density. This is how we got this equation here. So where we know that the total work done cannot exceed 25 kilojoules per kilogram, and if we are operating at 1.2 rho of 1.2 kilogram per meter cube of air, in that case, what is the total pressure possible? Rho times this work done per kilogram. So 1.2 times 25. That's how we get the 30 kilopascal number. Okay. So it's important to understand that the work done on gas is basically coming from the pressure volume energy effect that we have studied earlier. Okay. All right. So let's now look at fan pressures. We had used fan total pressure in this formula here, PT, but we haven't really fully understood what that means, or we haven't really fully defined what that means. So when we said it shouldn't be more than 30 kilopascal when we are operating in regular atmospheric air conditions, where is this 30 kilopascal measured? So we'll try to make an understanding of that here. So the total pressure is the line that is shown here in green. Okay, total pressure is basically, if you remember, a pitot-static probe. Total pressure measures, the pitot-static probe measures both the total pressure and the static pressure. Okay, so total pressure is the total energy in the system. It's the pressure corresponding to the total mechanical energy in the system, and it's a sum of the pressure energy, which is the static pressure energy, plus the dynamic energy, which is the velocity pressure. Okay, so velocity pressure is usually half rho v squared, right? Where v is the average velocity. And static pressure is if we have a static pressure sensor, it is measured by that. Whatever that pressure measures is the static pressure. Now, if you look at the fan in an airflow test chamber or fan test chamber, okay? So typically fans are tested in an airflow test chamber like this, okay? And you have a certain flow rate Q, and it's, let's say it's meter cube per second. It's basically volume flow rate, okay? Or it could be in cubic feet per minute. So that's flowing through here, okay? And it's coming out this way. So it's the same Q is coming out this way, especially if there's no change in density or there's no change in temperature, then the Q is the same, okay? Volume flow rate is the same if it's not compressible. Now, how will the pressure distribution, uh, how will the pressure be distributed from the inlet to the outlet of this airflow test chamber? For the flow to happen, there has to be some delta pressure, right? Typically, when you have a flow through a pipe and you have a certain Q here, typically P1 is greater than P2, right? Because there's a high pressure, it drives the flow. In this case, because the work generating device is in the middle of the duct, the pressure distribution looks something like this. It's not decreasing constantly. It's actually decreasing from the beginning until it reaches the fan, where it's the lowest pressure, and then it jumps to get the um, highest pressure, and then it goes all the way back to the same pressure. So outside is P atmosphere. Okay, let's say P atmosphere is 1 atmosphere. So let's assume 1 atmosphere outside the test chamber. Okay, so if you start at 1 atmosphere, you'll finish at 1 atmosphere. Okay, so there is no velocity here, v equal to 0. So there's the static pressure is same as the dynamic pressure. Okay, Sorry, same as the total pressure. Now, as the fan is rotating, it pulls more air, the velocity keeps increasing, okay, and the velocity reaches a stable condition and it's constant after that. The total pressure keeps decreasing, static pressure keeps decreasing as the flow goes through the from left to right. And when the fan sees the flow right across its blades, it puts in a lot of energy into the flow and increases the pressure. Now, the fan total pressure, P total, is different from all the P total here, or the TP. P total is defined as this difference, okay? This jump. You see this jump here? This jump has to be less than 30. What was the number we looked at here? Has to be less than 30 kilopascals, okay, for it to be considered a fan. And typically that's too high of a number. We are typically talking about 10 to 100 pascals when you're talking about fans used in refrigeration, right? So, and in air conditioning, maybe hundreds of pascals. So it will never reach a compressor level pressure change. So that's the first variable to define, total pressure. So the change in the total pressure energy before and after the fan is called the fan total pressure. Now, how do we define the static pressure? Is it this total change in before and after of the static pressure? No. It's basically you have to find the fan velocity pressure first. So you need to measure the velocity of the flow here, find the velocity of the flow here, and measure half rho v square, okay? So whatever that fan velocity pressure is, then you subtract that from PT. So measure the velocity pressure and subtract that from PT, you get the fan static pressure. So it's based on this delta here. So this is the fan static pressure. It's not the difference between this and this, okay? So the main variable is the fan total pressure. Fan static pressure is derived using that. So the thing you have to measure is the total pressure before and after the fan, and then the velocity of the flow after the fan. That's the variables that are used to define a fan's performance. Speaking of performance, this is a typical fan performance curve. So what are the items here? It has total pressure, which we just discussed, fan total pressure, and it's plotted against different flow rates. Okay, so there's a pressure graph here and it's plotted against different flow rates. There's also a power um, y-axis and an efficiency y-axis. Okay, so the pressures are all on the left axis um, on the pressure axis. So the fan total pressure, which is this guy here, the highest pressure in this graph. The second is the static pressure, which is this guy. And then there's velocity pressure. It's probably not shown here. It's basically the difference between these two. Then there's the fan power output, the energy that the fan gives to the flow. So that is basically not shown here. You have to derive it by multiplying the Q value to the PT value. So for any given Q, you know the PT value. Now multiply those two. You'll get the fan power output, the power going to the air. Fan power input is the electrical power, okay? So it's typically keeps on increasing with higher flow rate. Total efficiency is basically the amount of power you're giving into the flow to the amount of power you need to provide to the fan. So that's that fan total efficiency. Okay. And then there's a static efficiency, which is you calculate the total efficiency and multiply it with the pressure ratio between the PS here and PT here. Okay. So that's what the fan static efficiency is. So these are some of the typical numbers that the suppliers provide you with. The most important ones are you do need to know the fan power input, and you also need to know the fan total pressure, right? That curve. So if you have those two, um, you can calculate most of the other things. All right. Okay. So here's an example of um, the pressure versus flow rate curve that the suppliers provide. So not all the time they will provide total pressure. They'll provide static pressure too. And the reason for that I will explain towards the end of the slides. So static pressure curves with respect to volume flow rate. Here they are providing it for two different um, flow rates, two different RPMs of the fan, 800 RPM and 1000 RPM. The higher the RPM, the more the pressure, okay? So it can generate more static pressure. Like if you have a fan operating at two different speeds here, the the jump in pressure will be more for a higher speed, okay? And it will also help you move a lot more flow rate. So eventually the curves are going to be higher in pressure, and also they will go to a higher volumetric flow rate too. Okay, so two different RPMs of the same fan. This is how the curves look like. Just pay attention to this region, okay? This is called the stall region. Stall region. I don't know whether you're familiar with um, aerodynamics, um, but you know that when a plane flies, okay, there's something called angle of attack, okay? Angle of attack um, with the airfoil. And after a certain angle of attack, um, at alpha greater than alpha critical, then there will be a stall. Okay, there will not be any more lift. The flow separates. Flow separates from the blades. Okay, and what will happen is it is not able to generate good flow. There's a lot of turbulence, so you don't want the fan operating here. This is a bad operating region. Every fan will have a bad operating region like this, typically at really low flow rates, okay, and higher pressures. So you want to operate in this good region. So when you buy a fan and you're using it in some condition, if the pressure drop puts it in this region, then what you'll have is you have very unsteady flow, a lot of noise, and you will not be able to be sure what is the flow rate you're getting. It will switch back and forth between high and low flows and will be very unsteady. Okay. All right. Now, there are several types of fans. As you saw in the first slide, I had shown different types of pictures there. How are they classified? They're classified based on the directional flow. Okay. Axial fan means flow comes in axially and leaves axially. What is the axis? Axis means axis of rotation. Okay, so the axis of rotation is this red line, and the fan is rotating, the blades are rotating on that axis. And if the flow is flowing in parallel to that axis, then it's called axial fan. It's a radial or centrifugal fan if the flow comes in axially and leaves 90 degrees radially. Okay, if the flow comes in axially and leaves in at an angle much less than 90 degrees, then it's called a mixed flow because it's neither axial, it's not radial. And then there's another one. In this case, the axis of rotation is into the slide, okay? And the flow is normal to the axis of rotation, okay? It's basically going cross to the axis of rotation. So it's called cross flow fan, okay? So it's tangential or cross flow fan. All right. We don't have to go in deeper into this, but there are two parameters called specific speed and specific diameter, which are non-dimensional numbers, right? Um, that you can calculate based on your specific requirements. Here, n is the rotational speed. So if you want a fan rotating at a certain speed, and you want it to provide a certain flow rate, meter cube per second, and you want a certain delta pressure rise or the fan total pressure, and you also know the space requirements, you want a certain diameter option for that fan. If you know these numbers, you can calculate something called specific speed and specific diameter. Once you have those two numbers, put that on this chart called the Cordier diagram. Okay, if you happen to have those numbers land here, what that means is you need a radial fan. Okay, if you happen to have those numbers land here, that means you need an axial fan. Okay, so if your number lands somewhere in the middle, you may be needing something in the middle. Okay, like a some fan that is somewhere in the middle. For example, a mixed flow fan. So basically, this is very empirically correlated relationship, this chart, and it's basically trying to give you an understanding between fans that deliver higher pressure versus fans that deliver higher flow rate. Okay, there are radial fans. Radial fans give you more pressure at lower flow rates. Okay, it's not always true, but they are good for high pressure. Axial fans are good for higher flow rates and lower pressure. Okay, that's what this diagram basically is about. Okay, so if you're somewhere in here, um, you're delivering more pressure for the same. If you're using the same RPM, same diameter, everything, you're able to provide more pressure for that particular fan design. Okay, something that people use for selecting the type of fan for your application. A lot of times you don't really need this. You can you can develop the system curve for your application and then look at fan curves from all types of fans and see which fan will work for you. You know, you could do it that way too. And there are several softwares that can also help you select fans. All right, so let's look at axial fans. So like I said, axial fans, the direction of flow is same as the direction of the axis of rotation or parallel to it. So here are some examples. There are several different types of axial fans. Some are called propellers. Okay, so these ones, they produce really high Q but very low pressure. Okay, then there are tube axial fans, medium Q, okay, and medium pressure. And then vane axial fans, they produce medium Q and then higher pressure. Okay, so there are three categories. So you can see the propeller fan, if you look at the pressure volume curves, it can produce a lot of flow, high Q, but it's not able to create a lot of pressure. Pressure is low. Tube axial fans, it can create medium flow, but higher pressure. And then vane axial fans can produce a lot more pressure because you have some vanes that are static vanes that will, if you remember what I had explained to you, it will act like a diffuser where it slows down the flow and converts some velocity energy back into pressure energy. So it sacrifices some velocity or flow rate to gain some pressure. Okay, so there are several different types of fans. These fans are typically used in refrigeration for cooling condensers and evaporators. Here's an example of an axial fan. Here's another example of an axial fan. Okay, most of the time it's tube axial fan. Propellers are, when you look at a propeller fan, basically it'll look like it's almost fully open. Your ceiling fan is basically a propeller fan. There's hardly any pressure change that fan causes, but it creates a lot of flow in your room for cooling things in your room. Okay, but these fans, they have to overcome some pressure, so they don't you won't see that much open area in these fans. Okay, they're mostly they have big blades, so they have to overcome a lot of pressure. All right. Radial fans. In radial fans, we know the flow comes in axially and then they leave tangentially or radially out. Okay. Um, so there are several different types based on how the blades are arranged with respect to the axis of rotation. So if you're rotating, um, in all these cases, we are rotating counterclockwise, and if the angle of the foil is backwards, then in the direction of rotation, then it's called backward curved, right? In this case, the blade is actually an airfoil blade, so it has an airfoil shape instead of being a flat blade like that, right? So then you have an airfoil, backward airfoil. If you have a straight blade, sorry, a curved blade with no airfoil shape, you call it backward curved. If it is just a straight line but inclined backwards, it's called backward inclined. Then you have a blade where it's curved in the beginning, but towards the end it becomes radial. Okay, it's radial here. If you look here, it's radially inwards. So in those scenarios, it's called radial tipped. Then you have forward curved and fully radial blades. Okay, these are the 6 types of common um, radial fan blade types. And you can see several examples used in refrigerator. You can see this particular fan is feeding into a duct. So a typical axial fan, you will not use it this way because inside a duct, there's a lot of pressure drop. But these fans can handle a lot of pressure and deliver a decent amount of flow rate. They sacrifice flow rate for pressure. Okay. All right. So evaporator fans in refrigerators, flow ducts in refrigerators, and HVAC. That's where they're mostly used. Um, they're used as a blower fan in HVAC because in HVAC you have several ducts inside the house, so an axial fan will not be able to generate that pressure. Okay. Here you can see a comparison of the same RPM, 1140 RPM, between different blade configurations. Typically, the forward curved, this provides the highest flow rate, okay, and pressure. But typically, the backward curved airfoil, are the most efficient, okay. Um, these will draw a lot of current, but they do provide higher flow rate for the same RPM. All right. Cross flow or tangential flow fans. These are really inefficient fans, okay? But their main advantage is that they can be made really actually wide. They can be really wide. You can make them really wide compared to other fans, and it could be made for any width. So it's particularly useful for air conditioning systems, for split AC systems for the indoor unit, okay? So you have a long heat exchanger and you'll have a fan like this inside it. And this is the design. So in this case, the airflow comes in tangentially, right? And then exits also tangentially. And they almost always have a vortex inside. Okay, this creates noise and it creates inefficiency. But because of this peculiar feature of it can be made to really wide, it is it is used for such applications as air curtains and long and narrow heat exchangers. Okay, so that's its main benefit. If you have long and narrow heat exchangers, it can provide uniform flow along that length, which may be difficult with other fan designs to fit in there. Other than that, it's not a really good fan in terms of efficiency. Mixed flow fans, here are some examples of mixed flow fans. Um, they're not very common in when compared to axial and centrifugal, but they are there in some. I've seen them in some of the appliances in some refrigerators. Um, where they do provide some benefit, but typically it is more difficult to design the blades like this, and more difficult to manage the airflow paths. So their applications are very specialized. Okay, they're not very common. Here's a comparison of the efficiency value, the total efficiency values of different types of fans. Okay, um, so the backward airfoil is one of the most efficient in terms of centrifugal or radial fans. In axial fans, the vane axial fan is the most efficient, somewhere close to the same number. Tube axial propeller is one of the worst. Okay, and you can see the mixed flow is also not that bad, but the tangential one, it's really bad. Um, it's the one that I was talking here. It's full of turbulence. The only benefit to this is its particular geometric features. Okay. All right. Now let's look at system resistance. So we know how the fan's performance is measured. What are the performance metrics? But how is a fan selected for a particular application? So a typical application involves a typical airflow system application involves a lot of fans, and they also involve a lot of elements through which the airflow can pass. These could be ducts, elbows, expanding or converging transitions, heat exchangers, basically heating and cooling coils, air filter screens, guards. So there's a lot of pressure dropping devices through which the flow has to pass, right? You can see some examples here. Each component will have its own airflow resistance, and the fan must develop enough flow rate such that it can satisfy its primary function. And the primary function may be to cool um, a fridge, or cool a room, or cool a particular device. In those scenarios, it does need to provide the flow rate. It does need to provide the minimum required Q, overcoming all the um, pressure drops, right? Overcoming all the pressures. So we need to know what is the total pressure in the system first, as a function of Q. So P Q as a function of P, or vice versa, right? So if you have to provide a certain Q through the system, how much pressure drop are we expected to uh, see? That's what a system resistance curve is. So in a system resistance curve typically looks like this, depending on the system. So in this case, we have given you the least unlikely system, which is liquid aeration, where the pressure remains constant when the Q is increasing. That is least possible scenario. It never happens in air conditioning, but is a specific case where airflow goes through a liquid. Okay, for example, a aeration of sewage or molten iron, some specialty applications like that, where the pressure drop is always based on the weight of the liquid. So that doesn't change. Um, in all other cases, the pressure drop basically increases as the flow rate increases. Now it depends on whether it's laminar or turbulent. In most scenarios, we are talking about this rate of increase. It's quadratic. Okay, it's almost a square law between pressure and volume flow rate. So it'll be a curve, because in most flows that the fans are involved in are fully turbulent, and this is the pressure versus flow rate relationship. So a typical relationship, an airflow resistance curve for any system will look something like this. Okay. Um, if it is a fully laminar flow, which is not the case for most fan applications, in all the appliance scenarios for sure, it will be a straight line. And if it's partially turbulent, it'll be somewhere between those two, okay, slightly curved. All right, so how do we select a fan? So if you have a fan curve, which you saw earlier, that looks something like this, and you have a system curve that looks something like this, both of them are pressure versus Q, right? Pressure versus Q. You basically overlap them and see where they intersect. So the point where they intersect is the operating point. If this is the duct, okay, and the duct is giving you this pressure versus Q relationship, and then you have a fan, it's giving you this relationship. Sorry, I got it wrong. This is what the duct is giving, and the fan is giving this relationship. And together, if the fan is inside the duct, this is the flow rate you will end up getting at a pressure corresponding to this point. Okay. Now you can figure out what happens if you have a fan with a different RPM. Okay, you might get a slightly higher flow rate. That's here. If you have a fan, if you reduce the fan's RPM, you might hit here. Okay. If you add another resistance in your path, like if you add another air filter, you might have another pressure curve like this, and you'll reduce the flow rate. Okay, this is the flow rate direction. So depending on where you hit, it gives you a good idea of how to buy your fan, uh, whether it will serve the purpose for your application. Okay, so here basically I was showing you the effect of fan speed. So if the fan speed is increased, the fan curve will go up, and the place where um, the operating point intersects the system resistance curve will move to the right, so you'll get a higher flow rate. Okay, you might also, if you look at the fan power curve, the fan might increase in power a little bit also when that happens. And here, if the system resistance changes towards the left, um, it's increasing. Towards the right, the system resistance is decreasing. So depending on where if you increase the resistance, your flow rate will be lower. If you decrease the resistance, your flow rate will be higher, okay, because the point of intersection is here. All right. Okay. So now let's look at installation and system effects. Now, one thing to remember here is um, not always will we be able to operate at the exact intersection point. What happens is if you have a system, for example, let's say you have a system like this, a duct like this, right? Now, if you install the fan here, maybe you'll be able to achieve the exact intersection point between the fan curve and the system curve. But what if you installed it in a really bad way right next to the wall or right next to this wall? Then you will not be able to achieve the same characteristics. Why is that? Because the fan curve is developed based on tests done in a fan test chamber like this. Okay, so it's installed without any obstructions. It's installed in such a way where you can measure where the flow can easily go into the fan without any bends or disturbances. But when you install it in a very non-ideal condition where there is a fan is really close to a back wall or a wall in the front, right, where the flow is not straight entering or leaving the blade, then the fan curve does not represent the actual fan curve. Okay, so let's say your actual fan curve is number 1 here, and now in the system, when you install it, there is a wall at the inlet side of the fan, and that wall is at a certain distance, and based on the diameter of the fan, if the distance is, let's say, 35%, 18%, 9%, 5%, etc., right? So if that distance is 5% of the fan's diameter, you can see that the fan curve shrinks and it produces almost no pressure and no flow rate, right? If the distance is up to 35%, right? Um, then, so basically what I'm saying is if this distance is 0.35D, okay, then it's acceptable. So number two and number one are kind of close to each other. So this is acceptable, but any closer than 0.35, the diameter of the fan, makes it um, really bad to operate because now you're talking about the fan curve shrinking a lot. Okay, so 35%, up to 35% the diameter of the blade, you can have a wall. The same thing for the outlet. Um, you can probably get up to 18% or um, yeah, you could probably get up to 18% of the outer diameter. So you can be having a wall slightly closer than the inlet, okay? And you still won't have much of an effect on the fan curve. So if you don't see a big change in the curve, your operating point change might not be that significant. All right. Okay, so that concludes the lecture on fans. So we've learned about the power transfer to the fan, the definition of the fan, the important parameters for the fan performance, types of fans and their applications, and also the system effects of installing fans with system resistance. All right, thank you.